So let's get started.
Began according to plan as they leapt off the bridge while tethered to the cable.
Stand up. That's right. 1, 2, 3, go.
But as the team was about to reach the end of their first arc, the cable snapped, and 4 men and 1 woman plummeted 70 feet at 80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside, helmet cam. Kenny, myself, boy, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reach about 78 miles an hour, right about here, 78 miles an hour. You'll see the harness disconnect from the cable right there. Didn't see, just disconnect, my arm goes out, and here we come to the water. Kapow! Oh, like a ton of bricks. So look at the splash, like 40 feet. Pick your action now.
It's awesome action.
Began according
So a couple of
to
questions.
plan.
Going into full velocity right here. Probably reach about 78 miles an hour, right about here, 78 miles an hour. You'll see
How did you know that they were going to be going at 78 miles per hour? Right about there, he says it's about 78 miles
the
per hour.
harness disconnect from the cable right there. Didn't see, just disconnect, my arm goes out, and here we come to the water. Kapow!
And that's 91 miles per hour. How do I know that that's 91 miles per hour?
Oh, like a ton of bricks. So look at the splash, like 40 feet. Pick your action now.
It's awesome action.
Began according to plan. The team was about to reach the end of their first arc. The
78 miles per hour right
cable
there.
snapped, and 4 men and 1 woman
91 miles per hour right there.
plummeted.
How did they know that it was going to be 78 miles per hour? And how do I know that it's going to be 91 miles per hour? Furthermore, what do you suppose would have happened if these people decided to jump directly into water down below from a height of 270 feet? 270 feet is like jumping from a 27th floor of a high rise. Do you think that still would have been survivable? All right, so these are the questions that we will get to investigate. The first thing is first, we got to review. We're going to be talking about the conservation of mechanical energy. So what's energy? Energy is the capacity to do work. So the question is, what is work? Work is something that happens, it's a process of transferring energy. Something that happens when there's force causing displacement. So which means that there has to be an applied force. And then this force has to be responsible for the replacement of this object. Not the replacement, the displacement of this object. So there has to be an applied force causing displacement. All right, so from a mathematical perspective, it looks like this. So you've got this mass, there's force acting on it. Force is going to cause a displacement along the direction of r. All right, so force times displacement is going to be our work. So force causing displacement. So what happens when there's force causing displacement? What happens is the energy gets transferred. So work is the process of transferring energy. And work is something that happens when there's force causing displacement. All right, in this case, there's force acting on the crate, but there's no displacement, so no work is being done. So no energy is being transferred to the crate. All right, so there's force acting in the sky, and it's getting displaced along the direction of the force, which means that the work is being done on this person, so which means that the energy is being transferred to this person. All right, so work to exist, force needs to have a component on the direction of motion. Notice that the displacement is taking place in the horizontal direction, and there's force coming at an angle, and this force is a component on the direction of motion, which means that this force is directly proportional. This force is directly responsible. So let's discuss the meaning of positive, negative, or no work. If the force in displacement, actually the displacement, if they're in the same direction, the work is going to be positive, which means that the energy is going to be gained. If the displacement is in the forward direction, if the force is opposing that motion, the work is being negative. If they're in the same direction, the work is positive, energy is gained. If they're in opposite directions, the work is negative, the energy is being lost. In this case, the force is 90 degrees to the motion itself. This force doesn't have a component on the direction of motion, so no work is being done. Force and displacement, if they're in the same direction, the energy is gained. If they're in opposite directions, the energy is lost. And if the force doesn't have a component on the direction of motion, then no work is being done, so no energy is being transferred. All right, so lifting something up, the work is going to be positive. Force and displacement, they're in the same direction, so which means that in this case, energy is being transferred to the cat, so which means that the cat is getting energy. Carrying something forward at a constant speed in a straight line, just like this case represents, no work is being done because the force acting on the cat is there to balance the weight of the cat, and notice that the force is 90 degrees to motion itself, so no work is being done in this case. Bringing the cat down and putting the cat back down on the floor, the work being done here is going to be negative because the force is in the opposite direction of the motion, displacement, so which means that the energy is taken away from the cat of no work. So we know that the work is a process of transferring energy, so by the amount of work that we do, we transfer energy to the object. All right, lifting something up, the work is going to be positive because the force and displacement are in the same direction, so which means that the energy is being transferred to the object, so which means that the energy is being stored in the object. The amount of energy stored in the object is known as the potential energy. All right, here's the catch though. Let's take a look at it from a mathematical perspective. All right, so gravitational potential energy is the same as the amount of energy that you do. That's the same as the amount of work that you do against a gravitational force. All right, so effective gravity is going to be constant acceleration by lifting something up from the ground. which means that you're going to be doing positive work on this object, which means that you will transfer energy to the object by lifting it up. The amount of energy that's transferred to that object is known as the potential energy of that object. So it's going to become stored in that object. So it depends on the mass. It's going to depend on the gravitational acceleration. It's also going to depend on the height. All right, so higher up you go, the larger the potential energy of the object is going to be. So the gravitational potential energy is going to depend on the height. And you energize something by lifting it up against gravity. Let's focus on this one. This one is kind of interesting. So the car is speeding up in this direction. It's accelerating in this direction. Acceleration implies that there's a force acting on it, and notice that the force is in the direction of the displacement direction of the motion. So which means that the work being done in this car is positive, which means that the energy is being transferred to the car, and the energy appears in the form of motion. Right? So the energy in motion is known as kinetic energy, which is going to be related to the speed of the mass. V represents the speed, m is the mass. So 1/2 mv squared is going to be the kinetic energy that we're looking at. So that's the energy in motion. Faster something moves, larger the kinetic energy of the object will be. And then we got the mechanical energy. Mechanical energy is a combination of kinetic and potential energies. And mechanical energy can be constant if the work is being done by a conservative force like gravity. So if the potential energy goes down, the kinetic energy is going to go up. If the potential energy goes up, the kinetic energy is going to go down, provided that the mechanical energy is constant. So what conserves mechanical energy is a conservative force like gravity. So ignoring friction, the only force that acting on a system would be the gravitational force. If gravity is the only force, what happens is the mechanical energy remains constant. If the mechanical energy remains constant, all this potential energy will turn into kinetic just before impact. So that's what happens.
Again, according to plan.
Let's get back to the bridge.
Kenny, myself, Loy saw it. She does the front flip. Here we come, going into full velocity right here. Probably reached about 78 miles an hour, right about here, 78 miles an hour.
78 miles per hour. How did they know that it was going to be 78 miles per hour? All right, the cable is 200 feet in length, and that's all the information that I need. So how did they know that they were going to be going at 78 miles per hour? Let's figure that out. The first thing I'm going to do is let's draw this out. It's the pendulum move, the harness breaks at this point. This is the initial speed. This is the initial height. The initial height is going to be I'm going to measure the initial height with respect to the lowest point in motion, which is going to be right here. The initial height is going to be the same as the length of the cable. That's 200 feet. Initial speed is 0. Final speed is what I'm interested in. If done correctly, it should be 78 miles per hour. Gravity is the only force acting, so we will ignore friction, which means that mechanical energy is going to be constant. So we listed everything. The next step is conversions. Everything has to be converted to the metric units, so feet has to be expressed in terms of meters. So once we do the conversion, we end up getting that number. Everything is expressed in terms of metric units, so we're ready to go. But before we solve the problem, knowing that gravity is the only force acting, mechanical energy is going to be conserved. So final mechanical energy will be the same as the initial mechanical energy in this case. So we start our algebra. Final and initial mechanical energies are the same. Mechanical energy is a combination of kinetic and potential energies. So you got the final kinetic potential and then initial kinetic and potential energies. So write out the kinetic energy term, which is this. Potential energy is right here. Once again, your initial kinetic and potential energies. All right, so next step is before I do this numerically, I'll do it symbolically first. And then if I have any zeros, I'm just going to simplify the algebra. All right, so what do we know? Final height, I'm going to measure everything with respect to the lowest point in motion. So final height is going to be 0. So this term that we're looking at is going to go to 0. All right, so that is going to go to 0. Initial speed is 0. So initial kinetic energy is going to go to 0. All right, and now let's solve for the final speed. Get rid of the masses from both sides and then get rid of 2. And then come up with a final expression. The final expression that we come up with is straightforward. The final speed, according to this expression, only depends on the initial height. All right, so we got our numbers. Expressing the numbers in terms of the metric in the system, and then do a conversion to miles per hour. And then when we do that, we will get roughly about 78 miles per hour. So that worked out, that checked out. All right, so moving forward. The next question is, how did I know that they were going to hit the water at 91 miles per hour?
Stand up.
All right, so you go from 78 miles per hour. All 5 of them.
Recovering the memory of that fall will tend to their injuries.
All right, so moving forward. All right, so this is 78 miles per hour, and then boom, splash down. 91 miles per hour. Let's check to see how we come up with that number. All right, so algebra is going to be the same as before. I'm just going to set it up. I'll take it all the way to the top this time. Initial speed is going to be 0. Gravity is the only force acting on it, so acceleration is going to be constant. I'm going to measure the final height with respect to lowest point in motion, so it's going to be 0. I moved, it should be meters, not meters per second. So I didn't notice that I made a mistake. So I'm going to leave it there. All right, so this is 270 feet. This is the initial height is going to be measured with respect to lowest point in motion. You got a 200-meter cable and a 70 feet drop. So that's where we end up getting the numbers from. So expressed in terms of meters. Initial and final mechanical energies will be constant because gravity is the only force acting on it. So I'm going to cheat at this point. I'm going to use the same solution. Solution is a process of solving a problem, otherwise known as a derivation. So initial final mechanical energies are the same work, which means the final speed is only going to depend on the initial height. This time the initial height is going to be 270 feet. All right, so plug the numbers in. We get an expression in terms of meters per second, converted to miles per hour. That's going to be roughly about 91 miles per hour. So we end up getting 91 miles per hour. So things worked out. Having said that, I kind of alluded it briefly, so I'm going to go back to it one more time.
We reach boat. Only Kenny injuries are also severe.
All 5 survived. They hit the water at 91 miles per hour. 2 of them end up fracturing their necks.
The other
A bunch of them end up breaking their ribs.
injuries are also severe.
1 person survived without any injuries, 91 miles per hour. So 5 survivors. The worst case scenario, all 5 end up surviving. All right, so the next question is, what would happen if these people were to jump directly into water, a distance of 270 feet? Do you think that would have been survived?
Says he's trying to convince the city of New York to allow him to jump off the Brooklyn Bridge.
Visually, for me, it would just be so amazing to see somebody falling straight down into that water, knowing the dangers that exist.
So David Blaine wants to jump to Brooklyn Bridge.
That's 135 feet up.
That's half the distance that we're looking at, 135 feet up. Our distance is 270 feet.
A common suicide route.
Once you get beyond 135 feet,
This guy's a medical doctor.
your chances of survival are very slim.
He says, more than likely, you're not going to survive.
No, I won't die.
David Blaine says he won't die.
How do you know?
Good question. How does he
I
know?
won't. I'll make sure of it. I'm going to train and practice and prepare until the point of where I know that, you know, besides wood floating by or anything like that, I'll be safe.
He feels he will be safe, 135 feet. He feels that that's survivable.
Once you get beyond 135 feet,
And the medical doctor says,
your chances of survival are very slim.
so who's right? Who's wrong? How about 270 feet? I'm doubling the distance. What do you think is going to happen? All right, let's go back and run the numbers one more time. The worst case scenario. All right, so what would have happened if these people decided to jump directly this distance, 270 feet from the bridge? How fast do you think they would be moving? All right, so this distance that you're looking at is the same as this distance, which is going to be 270 feet. Everything is the same. So the final height is going to be measured with respect to the initial, it's going to be measured with respect to the water level. All right, so the initial height is going to be the same in both cases. Gravity is the only force acting on both cases. And the path of motion is not going to matter. If you actually do the calculations, the only thing that matters is the initial height. And because the initial height is the only thing that matters, in both cases, you're going to hit the water at 91 miles per hour. So if this is 91 miles per hour, that's also going to be 91 miles per hour. So in both cases, it's going to be 91 miles per hour. The only difference between this scenario and that scenario is this is going to take a lot shorter, and this is going to take a little bit longer. All right, so if you want to take your time and do a little bit of sightseeing, this is the way to go. If you're in a hurry, this is the way to go. Either way, you're going to be able to survive. So in both cases, the worst case scenarios are going to survive.
It was a good idea. I would think I should record it, but I don't.
This is a 5-second video.
It's doable, Sean. It really is. I have no reservations other
I've done the calculations for this
than
one.
my own fear.
Dude, make a reservation on the Born to Lose plane.
This is 410 feet.
Man, use your freaking
And you hit the water at 112 miles per hour.
flyer.
Ends up hitting the water with his back first and fractures it and survives. So 270 feet in the worst case scenario is still survivable. 135 feet, it's an illusion of danger. That's the reason why David Blaine calls himself an illusionist. I'm Ken Jaimas, and this brings this presentation to its final conclusion. Thank you for watching.